hopefully super fast. We are going to introduce go into the next chapter, which is exponential and logarithmic functions. Yay! All right, it's one of my favorite concepts to teach. And we're going to take 3-1 slow because we did our little half day of a test right now and only give you two concepts in a real basic worksheet that I just gave you there. But I want to tackle the 2 out of 5 components that they cover in 3-1 because of the review idea that we've seen this before, fumble, and we're just refreshing your memory on stuff. By the way, remember that book of functions that we don't really look at anymore? All right. Input, I say input, you say output. So one of our basic functions, it was y equals e to the x. And I said, you know what, just make it y equals 2 to the x. And then we can look at the pattern of what the graph looks like. And then from this, we know all exponential functions have certain ideas. So the first thing is, what's 2 to the 0 power? What does that equal to? 1. So when I plugged in 0 for x, I got 1 for y. Input, output. The most basic idea of graphing that I still think some people in this class still don't know how to do or make these pictures. So hopefully we get more and more people on the bus because this is how I want you to approach the worksheet and how you should think about graphing. Even if you have patterns and ideas of what's happening, you can always check, does input output check out? Does my graph make sense? What's 2 to the first? I'm plugging in 1 for x. Well, everyone knows that's 2. So then this thing starts climbing. And then when you put 2 to the second, now this is when the numbers start getting crazy. 2 to the second, not real crazy, 4. But then 2 to the third is 8. 2 to the fourth is 16. The y's start taking off enormously. So there's that exponential growth component that we should remember happens with this kind of scenario. If I raise 2, like if I made 2, 3, 4, 5, of course an increase in the base, increases how fast this goes up, but a general idea of what's happening here should be understood. If I had 5 to the second is already 25. So it would be 2 comma 25. All right, it'd just be a steeper graph. All right, but then what happens weirdly on the other end? What's 2 to the negative first? If you say negative 2, we got a problem. All right, what's 2 to the negative first? 1 over 2, the whole negative exponent rule. So I do have problems, but how do we not understand this? This goes back to being numerates and knowing your basic skills from previous classes. Of course, 2 to the negative second is 1/4. What is never going to happen for y? What is never going to happen on this side? It could never end up equaling what? 0. Even 2 to the negative million is 1 over 2 to the millionth. 1 over 2 to the millionth is almost 0, but it's not. So we get annoyed by that. So what do people do when they just don't want to keep showing that behavior of getting closer and closer to the y-axis? We draw an asymptote. The asymptote isn't there. We draw it as a boundary to say, just like in exponential functions, what we just had a test on, we're tired of getting closer and closer to the y-axis. Let's just draw a boundary there and then show that behavior. So all exponential functions have a horizontal asymptote. Okay, and we just got to realize where it's at by how we're looking at the picture. There is no vertical asymptote here. This graph does continue to go up and out. It just goes very steep. Right, so don't think that, especially when we're going into logarithms. And then I haven't done this, but what happens if I do this? And let's keep a base of 2, but what happens if I make it a fraction? Because now we want to really start thinking about that when we're looking at the graphs that we have to do on our homework. Well, it should be pretty simple. And I'm not going to write these down. We're just going to verbalize them. What's still 1/2 to the 0 power? I plug in 0, what do I get as an output? I still get 1. Anything to the 0 power is 1. But now what happens when I plug in 1? What do I get for an output value? Oh no, my first hour never talks to me. They hate me. What happens when I plug in 1, class? I get half. What happens when I plug in 2? I get what? 1/4. Let's go over here. I'll write this one down. What happens when I plug in -1? Flip. You get 2. So now it's -1 comma 2. This is just math 101. This is the basics. Okay, input, output. This tells me that this graph is almost identical to the other one, except it's, you could really call this a flip. A flip over what axis? The y. Okay, but we don't necessarily want to think of it that way. Here's what we want to know, or what we should get out of this. When I have a fraction raised to a power, the graph is going to look like this. The asymptotic behavior happens on the right side of the y-axis, not the left. It really is flipped. You know why this is flipped? This could be rewritten as this. And then probably getting into this too much, but isn't that the same thing as 2 raised to the negative x power? And then take the negative power, and then 2 becomes flipped to 1/2. And a negative on the inside of a function is a y-axis reflection. Okay? All right, so how do we attack this? Well, I just had that one. All right? And I'm going to use this as an example, but we could rewrite this, or we could just input, say it, output, and then figure out where our asymptote is through this idea of what we just talked about. So, for instance, this should either be before or after. You don't have to do a chart of values. Eventually, we should know by transformations where our asymptote is and where our 0, 1 coordinate ends up. Well, what happens when I plug in 0? What do I get? Well, hopefully you understand that this is an exponent. That's 2 raised to the negative x, and then -2 on the outside because of parentheses. So I used our book's software to show that, and sometimes they don't show exponents very well. We're now in the exponential chapter, so that's an exponent, so be aware of that. That just doesn't say 2 times negative x. All right, but what happens when I plug in 0? I get, I don't know where to write this. I'll write it off here. What's 2 to the -0? Does that really mean anything, or is that still what? What's 2 to the -0 power? 1. But what's 1 minus 2? -1. So really what you want to do is figure out where did that 0, 1 coordinate go compared to the parent function. That is the most crucial and important point because it's really close to the asymptote. All right, that's number 1. So the asymptote's close. And then we can find maybe this point and this point to see the behavior going on there. So, and this is how I treated input, output. Oh boy, back in the day when we talked about transformations, and it's really how we should be thinking. So, what I should do is 1 away from each of these and see what happens. What happens when I plug in a -1 into a negative x? What does that become? Doesn't it become 2 to the first? No one answered, right? What's 2 to the first minus 2? What does that become? 0, -1, 0. And then 1. Now here's where we get this. What's 2 to the negative first? What's 2 to the negative first? 1/2. What's 1/2 minus 2? What's 1/2 minus 2? It's -1.5. And then this is where we're starting to get those decimals. So 1 comma -1.5. Okay, so now here's what we should think. Okay, this is the same thing as this. So really what kind of graph I have is this one. Okay, it goes like that, and the asymptotic behavior happens on the right side of the graph. And it shows up in this fraction as I keep plugging in 2, 3. Don't plug them in, but just think about it. I plug in 3, that's 2 to the -3rd, which is 1/8. 1/8 minus 2 is -1 point. So we're getting closer and closer and closer to -2. Oh, okay, this makes sense. What does that -2 do? What does that do to a graph? It pulls at what? What does it -2 in a function do on the outside? Pulls it which direction? Down. Down how many? 2. So now it makes sense. The asymptote is no longer, sorry I didn't draw it at this, it's not at y equals 0. It's now at y equals -2. And that's how you come up with stuff. This is why input-output can always save you. It always makes me sad, students that want to be robots. And how do I graph an exponential? What are the rules? Don't get stuck with the rules, all right? You could always be saved by a firmer understanding of the concept. All right, and then domain and range, and then I guess some limits we could write here. Domain for exponentials, I shouldn't have to teach that. We can plug in anything we want for x, and then, evaluate. But the output's limited, all right? And the output's limited to what this asymptote did. And the boundary is now at -2. And notice this is not a bracket. It's a parenthesis because you can approach -2 but never cross it, the idea of how things evaluate here. And then you can do end behavior limits, and it does end up being a good thing. As x approaches infinity, what does my y finger approach but never get to? What number? -2. Okay, but then as I plug in negative infinity, my y finger goes off to positive infinity. Okay, now you can think about input, output, and put a chart of values. You don't have to, but I'm just going to think where in this next one does that 0, 1 point end up for the parent? Where does it translate to? Well, tell me what the translations are. What's +1 on the inside do? It moves at what? Left 1. What's -3 do? Down 3. We should already know where the asymptote is. Okay, but I'm going to plug in -1. That's how I told you to do these back in the day when we were doing transformations. We could think of transformations, or it's the 0 of the parentheses is where the main parts of our function end up. So for this, again, these are the 3 points you want to find, whichever way this is going. You want to find out where the 0, 1 coordinate ended up for translations, and then 1 before and 1 after that, and you know the asymptote's close. Okay, so it's plugging in -1 that makes that happen, and then it proves the left 1 down 3. Because when I plug in -1, I get 2 to the 0. What's 2 to the 0, everybody? Or no one in first hour. 1. What's 1 minus 3? -2. So -1, -2. That 0, 1 point went left 1 and down 3. Huh? Okay, thinking of the parent. That's when they talk about transformations. And then if you wanted to keep plugging in points, it'd be 0 and -2. If you didn't, then all you'd have to understand is this is what happens next. Okay, this is, oh, nope, it goes up. And then this is the next point that went close to this asymptote, and the asymptote's at y equals -3 now because of the down 3 thing. But I can check that. -2, when I plug that in, that's 2 to the negative first, which is a half. Half minus 3 is -2.5. So there's the approaching of -3. As I plug in -3, -4, -5, this is going to become -2.8, -2.9, -2.999. Blah, 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 blah. Then 2 to the first is 2. 2 minus 3 is -1. So there's that 0, -1 that I proved. So the parent function was shifted left 1 and down 3, and that's where the new asymptote is. All right? Okay, and then domain and range, quite simple. For exponentials, your domain's always, you can plug in anything. You could take a number to any kind of power, positive, negative, fractional, doesn't matter. But the range is what the asymptote shows, right? And then now a little different questions. When x goes to infinity, y goes to infinity. When it goes to negative infinity, we're approaching that asymptote y value. Right. Then the last one. What's a negative in front of a function do? What does it flip it over? Which axis does a negative flip in front of the function? X-axis. We can prove this by plugging in points. By the way, what point would I plug in if I am going to plug in? It's not a necessity, but what point would I plug in to start off? Oh no, is anyone listening? 3. Okay, you plug in 3. Because that's where 0, 1. We're going to move right 3 and down 5. And this point's going to prove it. All right? Now, but you got to be careful on order of operations. When I plug in a 3, what's 2 to the 0? 1. But it's like this. All right? Then you got to snap a negative on it. All right? The negative is not part of the power if you're going to think about input, output. So this becomes -1 minus 5. Which is -6. All right. So that's weird. That's because 0, comma 1 got flipped over the x-axis, then moved right 3, then moved down 5. 3, 4, 5. And that proves what did I just do there? I plugged in 3 for x. I don't know why I went to 1. My bad, dogs. Okay, flipped. I didn't go right 3. I went right 1 for some reason. And then 1, 2, 3, 4, 5, 6. A little mistake there. So that proves that point. Proves it. Okay, and then it proves what we're going to see next when I plug in the next points, which is 2 and 4. When I plug in 2, I get negative 2 to the negative first. And then minus 5. Okay, this gets a little strange doing this way, and I don't suggest maybe input-output. You just know where the asymptote is. The asymptote is now at y equals negative 5 because of the down 5, and the graph was flipped over the asymptote. That's why it's down below it instead of above it. Okay, so that's what I would expect you to know, and maybe at least plug in this point so you know where the 0, 1 value ended up. All right, from the parent function. Because then what happens after this is this behavior. All right, the graph actually flipped over the x-axis means it looks like this. And I'm going to erase that thing that I just drew. Okay, so that's what it looks like if we didn't want to keep plugging in points. You don't have to do this. You know, I try to teach things. Oh boy, that didn't work. Try to teach things that it's more than just rote memorization of this is what I do when I have this type of function. That never works out, and some of us are still stuck in that brain pattern, and that's why we're having the problems that we have. All right, we got to make it more simplistic in our mind. Okay, and then domain, of course, is all real numbers. You know, and I just hope you're listening on range. We've talked about domain and range like forever. Looking at that picture, actually the range that's covered is negative infinity up to the asymptote, negative 5. Those are the y values covered, and that should not be an issue. All right, when we look at the limits, as x goes to infinity, here's where y goes, which is all the way down to negative infinity. When x goes to negative infinity, we're confined by that asymptote approaching negative 5. That boundary. Okay? And hopefully we got some good recollection of that or understanding. Then we can move on to, I have this as concept number 2. So they have 5 concepts in 3-1. I think we had good enough time for covering 2 of them. Now this is going to be great when we have logarithms. This kind of question I'm going to show you next. But I'm going to pretend you don't know anything about logarithms, which might be a good idea to think that, because it is a tough concept even though you did do it in Math 3. So how are we going to solve this equation right here? And I started off with a tough one. Okay, so go ahead and write that down. Again, the notation in the book's really bad. They don't do exponents very well. That's raised to the 7 minus 3x power. Okay, so just make sure you understand that when we have a book assignment tomorrow. Okay, and it's really based off of this concept that's real simple. You tell me in that square that I have up there, a rectangle, what does x have to equal? I hope you're listening, by the way. I see a lot of people not looking up here. So in that little rectangle up there, what does x have to equal? X has to equal 7, right? Because it's just we're human. We can just match patterns. Here, I'm going to give you your first logarithm equation of the year. Here we go. What's LO6? By the way, my G's look like 6s sometimes. Okay, log of x equals log of 24. What does x have to equal? You don't even have to know what a logarithm is. You just have to be a human being and say, I know I'm solving for this, and this is in this position, so x must have to equal 24. That actually is a way we're going to solve logarithms. If I have log equals log, basically we can drop the logs because it's common sense. Just like this should be common sense. Okay, I don't really know what this is, but I think x has to equal 7 so that they match each other, right? Correct? We can do we can solve a trig equation right now. All right, here we go. Oh, maybe not. Sin. There's no sinners in a public school. What's x have to equal? 12. Fumble. Thank you. I was waiting to see if someone would say something. So we just solved the trig equation now. Boy, this is exciting. I can see it in your faces. So what do we have to do with this? We got to get this to be equal bases. So what's 1/4? A number. It's 2 to the what? So that's what you have to do. You have to find something that 1/4 is equal to. By the way, this only works if I can get equal bases. If I can't, fumble, then I have to use logarithms. And that's what's going to be coming up in 3.3. Okay, so but right now that's not going to happen. Every question on your worksheet, you can get equal bases, but what you got to do is make sure you keep your equality. 1/4 equals 2 to the negative second. And that's got to be correct. Replacing something with what it's equal to. And then you drop them. Why? Because of what I just went through. Because of what I just said about solving like this equation, even a sine. I mean, just by looking at that, this has to be true then. If I just get rid of that thing that's there, then x has to equal 12. Well, since these bases are equal, I could just drop them and solve the remaining exponent. All right, but you can only do this if you get the bases equal. And then if you can't solve this from here on out, I can't help you. And this is where some of us are having problems. Don't complain about the class if you can't solve a basic equation. That's what I'm running into. All right, I lament over these things. You know what lament means? Complain. Do I change 3 to the negative x? Nah. I'm going to change 81. Okay, so let's take it slow. What is 81? I know it's 9 squared, but I got to get it in terms of a 3. So what's 81? 3 to the what power? Not third. 3 times 3 is 9. 3 times 9 is 27. We're getting closer. 4. You got to be numerates. You got to be able to figure this stuff out. Oh, and then that's still not good. So what does this become? 3 to the what power? What's one more rule I got to use? Negative exponent rule. Okay, so it's all based on rules that you should already know. All right, 3 to this power equals 3 to that. The only way that's true is if this equals that. And for work purposes, I want to see that usage of the rules and the changing of the bases. All right, and all that stuff. So I'd like to see every single step. So 2 concepts. One is graphing. How do we attack it? Then the other is solving an exponential equation when you can get equal bases. Because then you could just drop the bases because of common sense. It's really not a mathematical thing we're doing there. All right, we're just saying 2 to this power equals 2 to that, only if this equals that. That's a big mathematical concept you can use on many different types of questions. All righty then. I guess they're just tired in first hour. I shouldn't take it so personal.